We are extremely honored to have here Professor Andrea Ghez. She concluded her bachelor in the MIT, her doctorate in the California Institute of Technology, was a postdoc in the University of Arizona. Nowadays, she is a professor in the Department of Physics and Astronomy at the University of California. She has received many awards and honors, among which is the last year's Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy. She is the fourth laureate woman, standing together with Marie Curie, Maria Gopelmeyer, and Donna Strickland. Her trajectory and achievements inspire girls and women all around the world, including many of us present here today. I hope you enjoyed the seminar in such a symbolic day as the International Day of Women and Girls in Science. And now Thais would like to give a word on behalf of our committee. Thank you, Professor Andrea, for being here.
Oh, hi, Professor Andrea Ghez. I am Tays. It is a pleasure to meet you. Thank you so much for accepting our invitation. And perhaps you don't realize how much important your attention to a cause is. Now I'm speaking on behalf of the committee, Carla, Paola, Emmanuel, Rodrigo, and myself, we decided to create the Astroscientists, or how we speak in Portuguese, Astrocientistas, because we are angry. This is not a good time to be a scientist in Brazil. And of course, the crisis is even worse for minorities. So our idea, which started quite small, was to amplify or even create a support net just to show ourselves that we are not alone in this fight. Again, thank you so much for being here today.
It's my pleasure. I'm so happy to be here. And thank you for explaining the origin of your group. I think it's so important actually to have a community of women who are in the same position. I think that's in some sense an important part of what enables people to go forward, to have that community, that support network. It's certainly been a key part of my trajectory, is to understand my communities and to have different communities that support me both as a scientist and as a human being. So it gives me great pleasure to share with you the work that's been recognized, and to share with you as well the path. And I'm happy to talk about that more in the Q&A as well. So let me go ahead and share my screen here to get going. So I joined the faculty at UCLA 26 years ago. And the reason why I came to UCLA was that I was very interested in using the Keck Observatory in a new and different way. And in particular, to be able to get the sharpest images possible with this brand new facility at the time, in order to ask the question, is there a supermassive black hole at the center of the galaxy? And what we've been able to do over the last 26 years is to demonstrate, or to move the idea of supermassive black holes from a possibility to really a certainty. This is a project I will share later on that I envisioned originally as a 3-year project. At the time, I couldn't imagine that I would be doing this a quarter of a century later, but it is a project that has benefited tremendously from the development and advancement of technology. So it just keeps getting better and better in terms of what we can do technically, which has unveiled just a wealth of scientific possibilities in terms of understanding both the physics of supermassive black holes, in other words, how does gravity work near these exotic objects, as well as what is their astrophysical role in the formation and evolution of galaxies. So the first question I love to ask in starting talks like this is, how do you observe something you can't see? And of course, that is an essential question if you want to find and study black holes. Of course, we should also first begin with agreeing on what a black hole is. So black holes are regions of space where the pull of gravity is so intense that nothing can escape it, not even light. So you can't see them directly. But there are also regions where gravity has overcome all other known forces and forces the object to become the infinitesimally small object known as a black hole. They attract a lot of attention because, in a sense, they're predicted by Einstein's theory of general relativity, but they also represent the point in our understanding of physics that where things break down. We actually don't know how to describe what a black hole is because fundamentally we don't understand how to make the theories of gravity, which is what Einstein is so famous for, work together with theories of quantum mechanics. And presumably when we understand these two things, we'll be able to understand what a black hole is. In the meantime, there is the abstract notion that of a Schwarzschild radius, so it's, which isn't a physical size, but an abstract radius, which is really important both for understanding how to study black holes, but also the proof of black holes. So the Schwarzschild radius is the radius at which is the last radius at which light can escape from the object. So you can't take any observations from inside this radius. But from the proof of a black hole concept, the reason the Schwarzschild radius is important is because if you compress an object down to the scale of its Schwarzschild radius, then that's the point at which gravity will overcome all other known forces and the object will become a black hole. And the Schwarzschild radius is incredibly simple to describe. It scales directly with mass. So the more massive an object is, the larger the Schwarzschild radius. So then the question becomes, how do you create black holes? And in astrophysics, we talk about two very different kinds of black holes. We talk about stellar mass black holes and the supermassive black holes. And I actually think this is a lovely demonstration of the two different methods in which both science and astrophysics work. So in the case of the stellar mass black holes, which were thought of originally, they were thought of first from a theoretical point of view and then discovered observationally. And in particular, the recent LIGO detections have provided just fabulous verification for the existence of the stellar mass black hole. So the stellar mass black holes, stars that start their life off with more than roughly 30 times the mass of the sun, are thought to end their life as small black holes. And by small, I mean roughly 10 times the mass of the sun. So that's starting with theory and then confirmed with observations. Now, the story of the supermassive black holes, and by supermassive, I mean 1 million to 1 billion times the mass of the sun. This is a situation in which the observations led and the theory has come subsequently. And it was the observations of a small fraction of all galaxies, known as active galactic nuclei, or AGN for short, where, and these are galaxies which produce a tremendous amount of energy from their centers, their nuclei. This is a classic picture that's shown in at radio. It's taken at radio wavelengths, where you see two phenomena associated with this particular case of an active galactic nuclei. First, and most dramatically, there are jets of matter and radiation that are coming out from the center. So you actually can see on the plane of the sky the motion of these jets, as well as actually along the line of sight. So you can measure the kinematic energy that's in these jets. And so you know that there's a tremendously powerful central engine that's driving this phenomena. So that was sort of observation number one. Observation number two is that at the center of this galaxy, there's emission or radiation that's very unlike anything emitted by any stars or gas or dust. And it tends to vary on very short timescales. And so it was put forth or posited that what was happening is that there's a supermassive black hole at the center of these galaxies that are accreting through that short chill radius of the event horizon a tremendous amount of matter, and that process is also driving these jets of emission. So that was the origin of the possibility of supermassive black holes, but it was definitely an indirect argument. And AGN are roughly 10% of all galaxies. But nonetheless, this idea of these cases where they're creating a lot of matter led people to theorize that perhaps all galaxies harbor such supermassive black holes at their centers, and that in other cases, the black hole is lurking at the center simply because there's not matter falling through the event horizon. So it's being heated right outside the event horizon. Okay, so this idea that supermassive black holes might be a key component of galaxies emerged roughly in the 70s, early 70s. Now, or 60s actually. So if you're going to ask this question about the supermassive black holes, our galaxy is certainly the best place to look. Actually, let me comment on this last slide, one more thing. Our galaxy is the best place to look because it's the closest center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away. And if we could get outside our galaxy and look back, this is very much what our galaxy would look like. It's a flattened disk-like structure and has these beautiful spiral arms. And our solar system is roughly halfway out in one of these spiral arm-like structures. Now, our vantage point is in the middle of this galaxy. So when we look up at night, in particular during the summer, we see the plane of the Milky Way with all the starlight, especially if you're away from city lights. So certainly not a place like Los Angeles. This particular picture was taken in Hawaii on the Big Island. So you'll notice also that not only do you see the light from all those stars in our galaxy, but you might also notice there's this dark lane in the middle of the starlight. And that lack of light is because of the dust. So in our galaxy, not only are there a lot of stars, but there's a tremendous amount of dust. And dust is very good at blocking light, and in particular optical light. So light that has a wavelength that's effectively the size of the dust particles or smaller are really well blocked by these dust particles. So in the optical, where our eye detects, only 1 out of every 10 billion photons makes it from the center of the galaxy to us. But if we go to the infrared, in particular the near infrared, 2 microns, sort of just a little bit longer than what your eye detects, 1 out of every 10 photons makes it to us. So we can actually study the center of the galaxy. So the development of infrared astronomy was essential for studying the center of the galaxy. And of course, that's much more modern technology, developed a lot actually by military purposes, because night vision goggles are, for example, are infrared technology. Okay, so thanks to this, we have the hope of seeing the center of the galaxy. And what we're going to look for to demonstrate the existence of a supermassive black hole is we're going to look for direct evidence through the motions of stars. So we're looking at the gravitational influence of whatever is at the heart of the galaxy, so its mass, influencing the motion of the stars that are at the heart of the galaxy. Now, from Kepler's laws, we know that how these stars orbit is dictated by the amount of mass inside its orbit, and that you've confined that mass to the size of the orbit. So in terms of this proof of a black hole, what you're looking for is to show that there's a lot of mass inside a small volume. So you want to see the stars that are as close to the center of the galaxy as possible to make the strongest case for the existence of a supermassive black hole. So that tells you why I was so interested in getting access to the Keck telescopes. So the Keck telescopes were opened in the mid-90s, so just at the point I had started my faculty job, and these are the largest telescopes in the optical and infrared in the world. And the way we characterize these telescopes is by the diameter of the collecting mirror, or the primary mirror, which collects the light. And the diameter of each of these telescopes, there are actually 2 for Keck, is 10 meters. And that's effectively the width of a tennis court, to give you a sense of scale. In fact, even the technology to build such a large telescope was really radical and very new for the Keck telescope. Each of these mirrors is composed of 36 hexagonal segments, and there was a long and drawn out argument about whether or not you could even get segmented mirror technology to work. And in fact, that is part of the technological genius of the Keck telescopes at the time of their construction. In fact, and many telescopes since then have adopted this design. For instance, James Webb Space Telescope, which is about to be launched, has the same mirror architecture. And all the next generation of telescopes, such as the 30-meter telescope or the Giant Magellan telescope or the European extremely large telescope, also adapts that hexagonal structure. And I'll come back to that at the end. So we have these telescopes, and the reason getting access to a large telescope is so essential for this experiment, where you want to see the stars at the heart of the galaxy, is that the larger your telescope, in principle, the smaller your angular resolution. In other words, your diffraction limit corresponds to a very small angle, and that angle decreases as the diameter increases. Okay, so that's the theoretical expectation for these telescopes. But the problem for Earth-based telescopes is that the Earth's atmosphere distorts the light that's coming through the atmosphere. So the atmosphere is great for us because it allows us to survive here on Earth, but it is a total headache for doing astronomy and astrophysics from the ground. And it's kind of profound if you think about it, because the light from the center of the galaxy has been traveling to us for 26,000 years. And in the last 30 microseconds, it hits the top of the atmosphere and gets completely distorted. So I like to say these are like little bug splat patterns that we're seeing here. If there were no atmosphere, each of these 5 stars would be the size of the smallest structures that are dancing around due to the diffraction limit, and they'd be rock solid. Okay, so the atmosphere is the problem. So I've spent much of my career working on techniques for overcoming the distorting effects of the Earth's atmosphere in order to get to the theoretical resolution of these really large ground-based telescopes, because we have much bigger telescopes on the ground than anything we have in space. Okay. So this is an arena in which the technology and the methodologies have evolved tremendously over the course of this work. So we started off with very simple techniques, which were much more, which were hardware simple and computationally complex. In other words, you did all the work in post-processing. So we did that for the first 10 years. It was called Speckle Imaging. It worked, but basically corrected, it allowed 3% of the light to be in a diffraction limited, and then the rest of it was was basically providing noise to your experiment. So it was the first step. And then after that, adaptive optics came online, which is a hardware solution to this. And even the story here is super fascinating, because while astronomers were on the way to developing adaptive optics, a parallel effort was ongoing in the military. And of course, the military also cares about looking both up and down through the atmosphere, but the military has far more money and resources than astronomy will ever see. So the technology was much more advanced. So at some point, there was a decision to declassify this as the astronomical community was catching up to things that had already been figured out in the military. So in other words, why invest more federal money in this development when, in fact, the technology is already pretty well developed? So there was a huge jump forward in the late 90s when this happened. And then it was really a matter of adapting this technology for astronomical purposes. This animation shows very nicely if you take what's going on. So we were looking at an animation showing the 5 bright stars just with very short exposures that allow you to freeze the interfering effects of the Earth's atmosphere. If you take a long exposure, it just sort of becomes a fuzzy blob. And then with adaptive optics, you can actually see the stars. And inside the box in the middle of the image is where we think the black hole might reside. There's a fairly faint radio source. So it's not bright like the active galactic nuclei, but it had a spectrum that was somewhat similar. So already people were wondering, could this be like a wimpy active galactic nuclei equivalent? Okay, so that's why we looked there. This technology a key part of this technology for adaptive optics uses lasers. The lasers are necessary to tell you how to move the key optical piece to the hardware to allow you to undo what the atmosphere is doing. I can talk about this more afterwards if people are interested more in the technology, but it's pretty spectacular, and it takes advantage of a fluke of nature that where the atmosphere basically traps the sodium atoms that are deposited by meteorites. So meteorites coming down to the Earth disintegrate, and the sodium atoms get trapped in this 4-kilometer layer, roughly, at about 90 kilometers. So we shine these lasers that are tuned to a transition, electronic transition in the sodium atom, and we stimulate those atoms to shine, creating an artificial star. So we can use that artificial star to tell us how to move the key element of the adaptive optics system that counteracts or corrects for the distortions introduced into the wavefront by the atmosphere. Okay, so having done that, we've basically been able to image the center of the galaxy for 25 years. The first 10 years, it wasn't as sophisticated as the next. And then once adaptive optics comes online, we can, for the first time, take spectra and images at more than one wavelength, more than just 2 microns. So you learn a lot more astrophysically once adaptive optics comes online. This animation is actually 1/4 of the real estate of that tiny little box that we were looking at with adaptive optics on and adaptive optics off, and allows us to see what's been going on. Oh, and I should have mentioned, when I first proposed this experiment back in, I guess that must have been 1994, the first proposal was turned down because people actually didn't believe that speckle imaging at Keck would work because it was a segmented telescope. And then the additional comments were, not only do we not expect it to work, but you might not see any stars, and even if you do, you probably can't see them move. And we were only proposing to see them move in a line on the plane of the sky. We weren't even thinking orbits at the time, because I think we just didn't understand how well all of this would work. And even the simple thing was controversial. I think that hopefully tells you why I love looking at this movie, because it really captures how much better this whole thing has worked than we could possibly have imagined. When stars are captured with an image, it's trailed by a dashed line. So there are stars that appear not because they just got brighter, but because our technology got better, so that we could see stars that were fainter. And then once it became possible to measure these stars spectroscopically, they're trailed with a solid line. And of course, the spectroscopy is important for a number of reasons. First is that it allows you to get the velocity along the line of sight through the Doppler shifts. And then, of course, for the first time, you can actually ask, what kind of stars are these? They're not just test particles that are moving around in a gravitational field, but they're actually real astrophysical objects. And that has led to a number of really exciting questions. Okay, but coming back to the first question, is there a supermassive black hole? At the start of this project, you could tell that there was a lot of mass, 4 million times the mass of the sun, inside this circle that's shown here. And there was no at that point, the circle is so much bigger. I mean, orders of magnitude bigger than the Schwarzschild radius. So there was no convincing argument at that time that people could make that there was a supermassive black hole. And what this experiment has done is to confine that 4 million times the mass of the sun into a volume that's 10 million times smaller and corresponds to the size of our solar system. So if you think about it, in our solar system, we have one sun. At the center of the galaxy, in the exact same volume, you have 4 million times more mass in that same region. And this is this is what has allowed us to increase the evidence for a supermassive black hole by that factor of 10 million. Okay, so now we have the strongest evidence for the existence of a supermassive black hole, not only in the center of our own galaxy, but in fact anywhere in the universe. And so now the question is no longer, well, actually, let me pause. So that means that you've moved the case for a supermassive black hole from a possibility to a certainty, and the drive and the research is no longer to demonstrate the existence of a supermassive black hole, but rather to use the center of a galaxy as a laboratory for understanding both the physics and astrophysics of black holes. So there are two parts of this, or there are two main thrusts in the research going forward now. One from what I would call an astrophysical perspective, and then one from a basic first fundamental physics perspective. So let me start with the astrophysics side. In the beginning, when we just were measuring velocities and using velocity dispersions to show that there was a strong mass concentration there, at that stage, where our field was to ask, in terms of the formation of the black hole, which came first, the supermassive black hole at the heart of the galaxy or the galaxy? It was framed as a chicken or the egg, the classic chicken or the egg question, which came first, the chicken or the egg. But what we've learned since then as a community is that that's the wrong way to think about the problem. And the reason we've moved in this direction is because as evidence for supermassive black holes have emerged in other galaxies where we can get the mass, we see that there's a very strong correlation between the mass of the black hole and the mass of the central part of the galaxy, known as the bulge. It's always about 0.1%. And the scale of the bulge is so much larger that it's hard to imagine a scenario in which one would form first and then cause the formation of the other. So today we think that whatever formed the galaxy formed the black hole synergistically. It was a byproduct of that. Both of them were byproducts of a single process, and that there's some feedback mechanism that keeps the growth of the black hole and the galaxy in lockstep. So the wonderful thing at this point is that we have the opportunity at the center of the galaxy to look at the physical processes that might be taking place to enable that feedback or that regulatory mechanism to keep the growth of these two things in sync. Now, this part of the project has been particularly fun from my perspective because there are a lot of predictions for what might exist at the center of the galaxy. I don't know why this is pausing, but it's supposed to be playing smoothly. So one of the things that I love about this project, this aspect of the project, is that almost everything that was predicted to exist or that should be observed near the supermassive black hole has been inconsistent with the observations. And so this has opened up a host of new questions in so many different astrophysical regimes. So the center of the galaxy is actually quite rich from an astrophysical perspective. So let me give you just a taste of some of the problems or the contradictions that have arisen, which drives forward a lot of the new questions. So the first that was uncovered was the presence of young stars. And in fact, in the late 80s, people used the presence of young stars at larger distances to argue that the center of the galaxy couldn't possibly have a supermassive black hole, because a black hole has such strong tidal forces that it should disrupt any fragile molecular cloud that might be the initial materials for star formation to come out of. So you would expect star formation proceeds by big balls of gas and dust collapsing under their own self-gravity. But you need very high densities to overcome these tidal forces that the black hole presents. So one would expect, so the prediction is, now that we know that there's a supermassive black hole and that we're looking at a regime that's so much closer, remembering that tidal forces get stronger as you get closer to the black hole, is roughly 1 over the distance to the 3rd power. So that's a really dramatic increase. And given the presence of, or the gas densities that we see today, the gas densities would have to be 10 to the 11th times higher in this regime than we see today to get star formation to occur. And yet we see tons of young stars. The young stars, pardon me, are the blue-green things that you see orbiting here. So in fact, they're the dominant part of the population. Okay. I like to call that the paradox of youth. How do you get these young stars? How do you get star formation to happen in such an extreme, inhospitable environment? And one of the clues actually comes from the orbits. So the orbits get longer as you go to larger and larger distances. So you need to be patient to get the orbits not in that initial small box that we were looking at, but at the distances of these stars. But of course that has, time has passed. And the precision of the measurements are going up, which also allows you to see small curvature. So you're not seeing complete orbits out here. But you can solve for the orbits because you now know a lot about the mass, the properties of the black hole. You can just solve for the shape of the orbit now. And as this movie pulls back, you'll see that many of the young stars fall in a disk, a plane. And that actually suggests a formation mechanism, perhaps very much akin to how the giant planets in our own solar system might have formed, our own and others, by the presence of a very dense accretion disk in the distant past, or not too distant, because these stars are not that old. They're only a few million years old. The second interesting paradox here is that there are no old stars. So the old stars, or very few are old stars. The old stars are orange. And the prediction for the old stars is that these stars have had a lot of time to interact. Those interactions create what's known as dynamical friction, and that those things therefore should sink towards the most massive object in the system, which is the supermassive black hole. So you expect a concentration of old stars. And in fact, we've used this idea to try to look for the presence of black holes in other galaxies by looking for this concentration of light that's predicted from this dynamical process. But when we look at the old stars here, there's actually a dearth of them. So, what's going on? Why can't we see what we call, what's that extra concentration, which is known as a cusp? And then the third that is actually highlighted, the third problem that is highlighted in this animation are the magenta objects. These magenta objects are fascinating. They're objects where you can actually see the outer layers being torn off. So you can see the tidal tails spatially resolved, and to see those tails develop as the star or the object gets closer to the black hole and then become more compact as the star emerges. To get those tidal interactions to happen, these objects, and for these things to survive, the conclusion that we've come to is that these indeed have to be stars, but they're stars that are a factor of 100 times larger than anything we predicted to be there in the first place. Today, I'm actually quite interested in the idea that these might be the product of mergers, so binary stars, which most stars start their life off as binary stars. And through an interaction with the supermassive black hole, you can actually get these things to merge. And when they merge, they inflate, they bloat up. And so for a number of years, roughly maybe 10 to the 5th years, they're in this inflated state, which would allow such interactions to occur. So that's what we might be seeing. Okay. So that's the astrophysics. The physics side is we can now use these orbits to trace the gravitational field near a supermassive black hole, and in particular to look at the predictions of Einstein in terms of how space-time becomes warped, or in terms of how the space and time mix as you get closer and closer to the black hole. There are 2 tests that we've been particularly focused on. And these tests are only possible once you've seen an orbit go all the way around, because you really need to know the shape of the orbit before you can get into how gravity works, or another way of saying that. Yeah, I'll just leave it at that. So these orbits, in particular, my favorite star has an orbit of SO2, goes around every 16 years. It's my favorite star because it's the only star that has complete phase coverage with both imaging measurements and spectroscopic measurements. So it has the best control. It has the best potential. Well, actually, let me say it has the best. It's the best probe of the central potential that we have today. Okay, so the 2 things that we've been after, one has just taken place and one we're in the middle of. The first is to look at what's known as the gravitational redshift, the relativistic redshift, and that describes how gravity affects the wavelength of light as it emerges from the object and loses energy as it climbs out of the gravitational potential and makes it to your telescope. Okay. So there's a prediction it should be dominated by what happens at closest approach. So basically you have to wait till it goes all the way around, and the next time it goes through closest approach, you have the opportunity to make these measurements. And that happened in 2018. So 2018 was a particularly exciting year for us. And it confirmed Einstein's theories of general relativity. Then the next thing is what's called the precession of the periapse, and it describes how the object itself moves through space and time. So the object, because of these effects, shouldn't come back to the same place, but should precess. And in particular, precesses in what we call a prograde direction. In other words, it overshoots. So in time, this thing will rotate. So it's like a kid's spiral graph toy. This is actually a signal that will improve or increase as we move towards the furthest approach, the apoapse. But in fact, we're already starting to see a signal. And what's so interesting is that what's starting to happen, although this is not something that I would be confident enough to publish, is that at first blush, it looks like the object is moving in the opposite direction. And of course, to me, again, it's always so interesting when things happen that you don't expect. It's like all the astrophysical questions that happened when we first turned on, or not first turned on, but in recent years that I was describing earlier. So I'm particularly interested in this question of what's going on with the precession of the periapse. Is it physics, or is it that there's an accumulation of small errors or systematics in your analysis? Because you have to combine 25 years or 26 years now of data in a way that is rock solid and doesn't introduce any sort of systematic shifts or rotation, in particular of what's called the reference frame. Okay, so all of that's going on. We're super excited. And in addition to all of that, time helps, but also so does advancing your technology further. So today we use adaptive optics with a single laser, and it corrects, for reasons that I can describe if people are interested in, only roughly 30% of the problems in the atmosphere. So we've gone from 3% to 30%, but it means that there's more to go to correct for the additional piece that one laser can't address. So we're in the middle of a project known as Kappa at Keck. So this is a big collaboration with Keck Observatory to build this next generation adaptive optic system that would launch multiple lasers to try to more completely correct the distorting effects of the Earth's atmosphere. You're basically doing a CAT scan of the atmosphere. All of this is super important to get to adaptive optics on the next generation of telescopes. The larger your telescope, the more ineffective a single laser will be. In other words, the smaller the fraction that you'll get. So in other words, if we use one laser with a 30-meter telescope, we would not get 30%, but we would actually be roughly back in the early days of Speckle with only roughly 3%. So in order to mitigate what's known as the technical risk for these next generation telescopes, developing this next generation adaptive optics system on the current generation of telescope is a really important way that we can move forward. So in fact, one of the things I love about this Kappa project is that beneath it is also a collaboration of all the teams building these next generation facilities. So the TMT, the GMT, and the European ELT. So while you can think of these as competing projects, they're also collaborating on this technological development with the current generation of telescopes. This next generation is super exciting. These telescopes take years and years to build. So I've been part of the 30-meter telescope project for a long time. In fact, I can very much date when I first joined. I was very pregnant with my first son when I joined the project. It was the first inception of the UC Caltech version of the project. And that was 19 years ago. This project should be phenomenal. And again, it doesn't really matter which one of these telescopes you're talking about. It's just what a 30-meter telescope would do for your measurements of the center of the galaxy. So this animation shows on the left basically what things look like with the current AO. In the middle, it's what this next generation adaptive optics system is expected to do on the current generation of on Keck. And then the 30-meter telescope version of the center of the galaxy is on the right. And this really just emphasizes that we're today only seeing the tip of the iceberg, that there are many more stars at the center of the galaxy that we can't see. We can't see the typical star at the center of the galaxy because of what's called confusion. You're confusion limited. Just the density of stars is so high that you can't see the fainter but more populous stars. Oh, let me end by just giving credit to my collaborators. This has been a long project, so this picture shows me 26 years ago with my long-term collaborators, Eric Becklin and Mark Morris on the left, and my first graduate student, Beth Klein. But today, the group has expanded tremendously, mostly because the scientific opportunity within the data set is ever more expanding. So it's a data set that can be mined for many, many, many projects. And the project overall has become a key science case for the development of instrumentation at Keck and the 30-meter telescope. So we're a core collaboration of about 30 people and a broader international network of about 100. So let me conclude, if nothing else. I hope I've convinced you that there is a supermassive black hole at the center of the galaxy, and hope I've shared with you the excitement of what we've learned by both setting out to address a specific question, but actually unveiling more questions than answers. So thank you for your attention.
Thank you so much, Professor Ghez. This was a really nice talk, and now we we start with the questions. So please, you can raise your hand in Zoom. So first we have a question. Katarina, please, you can ask.
Hello, can you hear me?
Yes.
Yeah.
Okay, so thank you very much, Andrea. And I wanted to thank you for 4 things in this first moment. First of all, for being available to talk to us, the Brazilian community that is thinking about how we women work in astrophysics here, and to be able to see a talk from you that you are pretty much an inspiration for all of us in this day that is special internationally. So I'm very grateful for that. And I also wanted to thank you for your work. I work with galactic nuclei, and your videos that are simply amazing, these that you showed today, they really help me out to show people why is it important for us to keep on doing what we do. I would also like to thank you for being a role model, for being this inspiration for us as girls and women in science to think that we can make our dreams be possible. We have you as an example. And I would also like to thank you for an advice that you gave on another talk that I saw from you. And we asked you what would be an advice for young women in science. And you told us that we should use our challenges as opportunities to go further. And that really helped me out a lot individually. And so my question would be, how do you think this advice would fit in a more, in a wider perspective of women in science? What do you think are our next challenges and our next opportunities to overcome these challenges? Thank you.
Oh, thank you for your very generous and kind remarks. I really appreciate it. My favorite expression is every challenge is an opportunity. The older I get, the more I appreciate it. In a sense, you know, challenges force you to think more deeply about what's going on. Because if you go forward without any resistance, your thinking doesn't progress because you got through whatever you were trying to accomplish. So when there are obstacles in the way, I think it really forces you to think about, well, what's inherently going on? Like what's at the root of this? And not just what's in, like how it's being expressed, but how do I get around it? I mean, I'll give you a couple examples, really specific. I can't remember what talk you're referring to, and I don't know if I shared this already. But I have 2 moments in my development as a younger scientist that were really pivotal in my thinking and my understanding of that concept. So I remember when I was a first-year grad student and I had gone to my, you know, the first professional conferences, and there were a couple of instances of senior men asking me to go to dinner. Under the guise of, I want to understand your work better. And I remember coming back I was a grad student at Caltech, and speaking to a senior scientist at the time. She's a really important role model for me. Actually, her name's Anila Sargent. And she just said, and it was so perfect, actually. She looked at me, she said, look, they're going to be too busy looking at your legs to listen to your talk. So make it lunch, bring your preprints, and make sure they never forget what you work on. So to me, it was an interesting thing of not making it confrontational, but moving it to being more professional. In other words, the problem really was that it was, that the ask was not the professional ask in a professional setting. And it's a great thing. It's just like, anyway, it taught me an interesting device that didn't make an enemy of these individuals with whom I've had to work for many, many years. And it worked. I mean, of course that technique doesn't always work, but in those instances it did. And then many years later, I had another instance where something didn't work, and a senior person gave me advice that is effectively the same piece of advice. And the instance, which also pertains to being a woman scientist, but in a very different situation. I have two kids. So I have a 19-year-old and a 15-year-old. And UCLA has a daycare center, which is amazing. I have to say, I'm really grateful for daycare on campus, because for reasons that maybe I'll comment on later. And I couldn't get a daycare spot for my second kid. There's a prioritization, there's a list, you have to compete for it. I used to joke that it was harder to get a daycare spot than tenure. So I was denied the spot, and I was furious. I mean, I had just gotten elected to the National Academy of Sciences. I just thought, oh, come on, this is ridiculous. And this a colleague who he's unfortunately passed away, but I had really a lot of respect for him. His name was Mike Jura. He just looked at me and he said, look, write the angry letter, tear it up, and help people do their jobs better. And it's the same thing, which is like, there's a problem, but help people get to where you would like them to be. And so in the end, I wrote the more productive email and got the daycare spot. So I think those two moments were really pivotal for me in terms of understanding how to shift challenges to opportunities. And the opportunity for the daycare thing just ended up with me, ultimately developing some very nice relationships with senior folks at UCLA that are now helping me build a research center. So it really did become an incredible opportunity. And I guess in the first case too, those were relationships that became important professionally, as opposed to being complicated professionally. So I guess those are the things I could share. Good luck.
Okay, Professor, thank you so much. And now I think we are gonna pass to YouTube question. So Paola, please.
Yes. We had actually a similar question from Jessica Lemos, a similar question to Catarina's. So now we are going to ask the question for Maíra Cesário Alvinlobo. The question is the following. When you approximate the black hole mass using the trajectory of the stars, do you have to consider black energy matter?
Oh, so that's one of the things we never did before, but the idea that the object might be processing in a retrograde orbit direction could be explained by dark matter. So we've now added that to the model. And really the work is focused right now on trying to understand whether or not that's the correct interpretation. In other words, whether or not it's physical origin, in which case you would say it would be dark matter, and super interesting. Or is it that you have some problem with constructing your reference frame? So if you told me 25 years ago that I would be really interested in the topic of reference frame construction, I would have yawned. But now it's so fundamental to the measurement. If you have your reference frame drifting, that's going to create this apparent signal. So you have to be really clear on your systematic errors. So it becomes a little bit more like maybe one of these like a physics experiment where the real work, because you're making a precision measurement, so much of the work becomes understanding your systematic errors. So that's what I wake up thinking about these days.
Thank you so much. Now we can pass to a Zoom question.
Yes, Clara, please.
Hello.
Hi.
Hey, thank you so much for your lecture. I can't believe I'm actually talking to a Nobel winner. I'm really happy. First of all, I'd like to thank you because it's very inspirational to see someone who sees challenges as something so exciting. Every time you said like, "Oh, this is so exciting!" It raises so many questions. Like, this is amazing because problems are always going to arise, especially in physics. So we need to keep being happy by seeing them. And my question actually arose a little later as I was seeing your background. And I was wondering about the sodium atoms. And if there's like a very specific um, reason for using them, or if it's just because of the comets leaving them behind or something like that.
It's a question of what can you stimulate effectively with a laser, with lasers that are developed, and what's available. So that's the choice of the sodium atoms. It's that combination of what the meteorites actually deposit and what you can what kind of lasers that we've developed that are strong enough or powerful enough to stimulate something at 90 kilometers away to give you a star that's pretty bright. I mean, these stars have a magnitude of roughly 10th magnitude optically, so you're stimulating a lot of sodium atoms up there.
Thank you.
Okay, thank you, Professor Ghez. Now, Paola.
Yes, we have a question from Bruno Henrique Garcia Malvestiu. The question is the following. For you, what's the most promising area of physics, astronomy research for the upcoming years?
Oh, I think we are so fortunate right now because there's so many technological advances in so many different arenas. So, there are big areas that people are very excited about and therefore have really focused instrumentation on. So the development of instrumentation to detect the signatures of life on other planets, I think that will continue to be an incredibly big growth field. I think the continued work in gravitational wave astrophysics is incredibly exciting. I mean, the fact that they've worked for 40 years to develop this technology, and now we're seeing this incredible scientific return. And again, seeing things that don't always quite make sense. I mean, they confirm a lot of ideas, but they also equally raise a lot of other questions, like why are we seeing stellar mass black holes that are larger than what we expect? And why are we seeing the mergers happen slightly more frequently than is expected? So, and then of course that all leads into LISA, the space-based gravitational wave detector. And that will open up the mergers of the supermassive black holes, and presumably we'll have a lot, we'll learn a lot there. And then just the whole 30-meter telescope plot, that era or that class of telescopes will open up a large variety of fields. And one of them will be just understanding the evolution of galaxies over time. So I guess I'm a big believer in looking for two things, like new technologies, like what can new technologies open up, and then also following through and really thinking about things that don't make sense, or looking for the weakness in our explanation. We develop these theories or models, but it's useful to look at where those models are weak, are based on assumptions that could benefit from a little more poking with new technology. So I think we won't be bored as a community.
Yes, sure. Thank you, Professor. Tays, you could go.
Okay, so now we have Vivian. Vivian, please.
Hi, so I'm Vivian. I'm a transgender woman and a postdoc at the University of Arizona. And I just recently had the opportunity to participate in my first admissions committee and also by talking to other professors and as a postdoc trying to get faculty, I realized that the higher up we are in academia, not only there are fewer spots, but the more conservative committees become, citing arguments that have not that much correlation with what you actually have done, like fitting to the place or like and so how can we help change that, and given that most of us are either postdocs or students and not in positions that allow us to make decisions.
I think there are two ways of thinking about this. In a sense, one of the ways that we can make change is by doing the best research we can possibly do, by succeeding. And then the other is by getting a seat at the table, which you were mentioning, which is by getting a seat at the table for doing admissions. And I think one of the real challenges for minorities in any setting, which is that early in your career, it acts as maybe a downward force because you have to overcome people's skepticism. I think this is what you were asking, so pardon me if I'm on a track that you weren't asking about. But then once you become accepted in a sense by the field or the community as somebody they trust to put on committees, then you're going to be asked to sit on a lot of committees because everybody's looking for the minority to satisfy the diversity of committees. So there's almost overpressure. And I think the danger there early on in one's career is that takes away from your ability to do good research. Coming back to that first point, which is almost the most effective thing you can do is to succeed, right? The more people who do well and thrive and show that, you can do the science as well as anybody else is really the most important thing we can do. But then just getting a seat at the table and everybody has different viewpoints on this. I've always been interested in these issues, but when I was younger, it was mostly around how do you create communities and networks to provide, which is exactly what you guys are doing with this, right? To allow you guys to have the strength and fortitude to put up with whatever BS goes on. And to also have a community that you can develop strategies for dealing with it. And then as you get older and have more power, it's your responsibility to bring these up because there's less cost to you for bringing them up. Does that make sense?
It does. And by the way, it's an honor to be talking to you. I've seen a talk from you when I was still a graduate student at the University of Chicago. It was a great talk, and it's a pleasure to see you again.
Oh, thank you so much.
Yes, okay. So sadly, we don't have more time for questions. I would like to thank you again, Professor Andrea Ghez. And please, if you have time, look at the chat. People are giving really nice feedback and comments. And I just can say thank you again.
Oh, well, thank you. This has been an absolute pleasure. Good luck, everyone.
Thank you, Andrea. Nice to see you.
Yes, and you can thank Angela.
Well, next time, Tays, everybody, we have to take Andrea around in Brazil, wherever she goes, right? So you have fans, every city. We have, representation from lots of different towns. So you tell me, and we'll have certainly the VIP treatment in 3 dimensions. But thank you so much for visiting in 2. It's wonderful to see you. Take care.
Bye.
Bye-bye.